Yeah, so continuing with stealing other people's talks, I actually wanted to get you sort of warmed up for Stacy's talk, so maybe she doesn't have to give as much introductory material on quantum computation, and there's more time for thought and you know, uh, yeah, trying to come up with better schemes. Okay, so so here's encrypted cloud quantum computing. So yeah, I spent very long on this slide, as you could tell. I added the word quantum, and I changed a little bit how delegation is explained. So basically, the situation is that the server might have quantum computation, but Alice might be weak. Somehow she might be completely classical or have limited quantum capability. And what she wants to do is to still have this situation where she can encrypt her data, and the server can perform quantum computations on her data and send the result back, and she can decrypt. Okay. So, so the only problem is that the FHE scheme that we have now, which is called fully homomorphic, isn't really fully homomorphic in the sense that if you believe that quantum computers will one day exist, then really the computation we should be talking about is quantum computation. This is general computation, and right now we don't have an FHE scheme that handles general quantum computations. You can't just sort of take the FHE scheme that we have, where the messages on the operations on the messages are just addition and multiplication. I mean, that's not a complete set of operations for quantum computation, so you can't expect it to just operate directly on the cipher. Yes? Well, I'm not going to take too much away from Stacy's talk. She'll talk about what we know. I'm just going to talk about sort of what the problem is and get you sort of thinking about it. Yeah, I mean, yeah. So I'll let her talk. So I'll just describe the problem. So sort of another thing you can think about is like Shor's factoring algorithm. So like if you imagine, so even in the quantum setting, we can imagine that it should be efficient to run Shor's factoring algorithm, but we still have could have quantum resistant public key cryptography. So it's conceivable that we should have an FHE scheme where I can encrypt the modulus and you send it off to the server and the server can factor it for you. Okay. So I'm just helping Stacy out a little bit by describing like qubits and stuff. So she'll probably describe it again tomorrow, and most of you probably don't know that much quantum, so it's probably a good thing if you hear it twice, I think. So so basically the deal is that instead of bits, we have these things called qubits, which are just two-dimensional complex vectors which describe the state of this qubit. The alpha and beta there are complex numbers, and the norm of the vector is 1. And so you can think of this as sort of a basis. This is what the qubit is in the 0-1 basis. Okay, it's two-dimensional. And so if you measure in the 0-1 basis, what will happen is that the outcome the qubit will collapse to either state 0 or state 1. It'll collapse to state 0 with probability alpha squared, and state 1 with probability beta squared. Right. If you choose some other orthogonal basis to measure in, then the probabilities that it'll depend to phi or psi depend on the particular squared amplitudes of that vector in that basis. Okay. So you can have more than one qubit. So this is the general state of 2 qubits described by 4 amplitudes. The norm of the vector is still 1. And you can have states which are separable. So they can basically be described as a tensor of 2 separate states. And you can have states that are entangled, which are not separable. And so if you measure, and you can have a four-dimensional basis there. You have this four-dimensional basis represented by zeros and ones. If you measure in this basis, then the probability that it will collapse to state ij will be alpha ij squared. Okay. You could measure kind of sort of 1 bit at a time, 1 qubit at a time. And if you just like measure the first qubit, for example, then you'll get 0 with probability that. The squared norm of the part of the vector that's consistent with 0 in the first position. And the state will collapse to that, be consistent with that. Okay, so the amazing thing is that you can have n qubits, and in some sense, these n qubits represent a 2n dimensional amplitude vector, which seems pretty amazing. You can do manipulations of this vector, and people talk about this with great excitement. But really, maybe this part of it is not so surprising when you consider that just basic probability of over n correlated variables can also be described by a 2n dimensional vector, and you can sort of do computations on that as well. It's just basically we're basically doing probability here. Scott Aronson likes to say quantum computation is basically probability in the L2 norm. So there's classical is in L1. Okay, so the different types of operations that you can perform on quantum state. So if you want to modify it, the first way is what I mentioned. You can measure some of the qubits and it will collapse, and that you will lose some information in that process because it collapses. The second is a unitary evolution, which is basically you can perform unitary transformations, rigid motions on the amplitude vector to transform the state to another vector. Okay, and these operations are reversible. But to make it efficient, you have to sort of describe your unitary transformation, or at least this is not how we know how to do it. You have to describe your unitary transformation as a composition of very basic unitary transformations that operate on 1 or 2 qubits at a time. Okay. So these are the basic operations of quantum computation. So for classical computation, like I mentioned, basically addition and multiplication suffice. So here I'm going to describe a complete set of gates for quantum computation. So these are the basic gates that you see. There's I, which just leaves everything alone. There's the X gate, which kind of flips the positions of alpha and beta in the state of a single qubit. There's the phase flip, which changes the sign of beta in the qubit. And Y you can ignore since it's basically the product of X and Z. And these are the Pauli matrices. And then there's some other gates. So you can sort of rotate by a smaller amount in the second position there. Multiply the second coefficient by I. And then you can sort of rotate by an even smaller amount. That's called the T gate. And of course, there's the lovely Hadamard and various other gates. So actually, I won't get to that, so I won't use that. So those are 1 qubit gates. Those just operated on 1 qubit at a time. So to operate on 2 qubits at a time, so the state of 2 qubits is represented by a 4-dimensional vector. And so here's a C0 gate, which basically flips the positions of the 3rd and 4th coordinates. Right. So you have the universal set of gates. I mean, there are various universal sets you can take, but you can take, for example, just the 1 qubit gates and C0. Those are complete for quantum computation. Okay, and there's a Toffler gate. You can ignore that. Okay. So what I was saying about classical FHE is that it has this sort of commutative diagram aspect that the operations commute with the decryption operation. So just and I described how we did that in the classical setting, basically ring homomorphisms and then making them noisy. And the noise causes some problems, but you just find ways to manage the noise, and everything works. So, just to warm you up for Stacy's talk, I just wanted to get you kind of thinking, or maybe I don't think you'll solve it right now. But if you have a whole day, maybe by tomorrow you can interrupt Stacy's talk. Actually, we'll see. So, but I think this is a nice problem. That is, can you find some way to construct some quantum encryption scheme, whatever that means, where the decryption operation in this scheme somehow commutes with all these basic 1 and 2 qubit operations. And Stacy will describe something that gets us sort of maybe halfway there. And there's this pesky T gate, which is just a problematic gate. Well, she'll describe that tomorrow. So I just wanted to warm you up for that. So, okay. If you have questions.
So the dream is to be able to outsource quantum computation to the cloud. Yeah. Stacy's. So I guess we're not there yet, but getting there. I see. Okay. So actually, just to wake everybody up, let me ask you. Let me give you a puzzle. See if you were paying attention during Craig's talk. So here's a really simple FHE scheme. Everybody wake up. This is a challenge for you. We'll see who solves this. So here's a really simple FHE scheme, as simple as you can imagine. So you have a modulus, which is n equals p times q. The factor is a secret, n is public, and we're gonna work in the ring Z mod n. Okay. Now here's how we're gonna do encryption. Really as simple as it gets. So we're gonna choose two vectors, v1 and v2. They're gonna be secret vectors. This is gonna be the secret key. It's gonna be a symmetric key FHE scheme. So v1 and v2 are a secret key. The way we encrypt a message is as follows. We're going to choose a random R, and then we're going to output the unique matrix A such that V1 is one eigenvector with value M, and V2 is the other eigenvector with value R. So far, so good? That's it. That's the whole scheme. So the ciphertext is just a 2x2 matrix over Z mod N, and it's an encryption of M. If you know V1 and V2, it's trivial. If you know V1, the way you decrypt is you just compute the inner product of A with V1, and you'll get the message back. So decryption is trivial. If you know V1, decryption is trivial. The scheme is fully homomorphic, right? If I give you the encryption of M1 and the encryption of M2, if you add these two together, because both of them are using the same eigenvectors, V1 and V2, the eigenvalues will just add up, so you'll have M1 plus M2. And if you multiply two ciphertexts, the eigenvalues will just multiply. So it's fully homomorphic. Problem solved. So why is Craig torturing us with all these ideals? And here's a fully homomorphic encryption. Well, let's think about security. So if I give you the encryption of a random message M, I give you the encryption of a random message M, so I give you this 2x2 matrix. So it's an encryption of a random message M with a random R. How would you break this? Right? The way you would somehow have to compute the eigenvalues of this 2x2 matrix. But computing the eigenvalues of a 2x2 matrix requires solving a quadratic polynomial, right? You compute the characteristic polynomial, and you have to factor it, but you cannot factor mod n. Yeah, so you cannot find the eigenvectors of this matrix. If I give you the encryption of a random message M, you can't learn anything about M. Yeah, let's not worry about, absolutely. This would not be quantum secure. Okay, touche, yeah. This would not be quantum secure, but let's live in the classical world, so no factoring. So are we done? Like, is this a fully homomorphic encryption scheme? Can someone break this? What? Ah, excellent. There we go. There we go. Okay. So suppose perfect. So people are still awake. So if I give you the encryption of the same message twice, yeah, so different R's but the same M, then now you get A1 and A2. You subtract them, and you'll get the encryption. You'll get a A1 minus A2 will have 0 as an eigenvector, as an eigenvalue. So now you just find the eigenvector that corresponds to the eigenvalue 0. You have V1, and you've broken the scheme. Okay, so the scheme is secure, as we say, one-time secure. It's secure for encrypting one message, one random message, that is, and that's all. So here's but this is a really simple and cute scheme. Yeah, if you give me two encryptions, it's completely broken. And so this is kind of a cute puzzle. I mean, is there a way to make this 2-time secure? So can you kind of take this idea, maybe use 3x3 matrices, or I don't know, can you make this somehow 2-time secure? So if I give you the encryption of 2 random messages, it's secure, but or even if I give you the encryption of the same message twice, it's secure, but if I give it to you 3 times, it's insecure. And by the way, I'll say for one of the applications that we always think about for FHE, this is where I want to send, I want to send my data encrypted to the cloud, have the cloud operate on it, send me back the resulting ciphertext, and I'll decrypt. Those settings are exactly one-time encryption settings, right? I can generate a new public key secret key, encrypt my data to the cloud computes, sends me back, I decrypt, and I throw away that encryption decryption key. So really, the killer app for FHE is a one-time encryption app. So that's exactly what this does. It's one-time secure. Unfortunately, this is not semantically secure. This is not semantically secure. So it doesn't quite work for the outsourcing application. But maybe there's a way to make this semantically secure. So keep in mind that for FHE, really symmetric encryption and actually one-time symmetric encryption is enough. And there really are ideas that kind of come close, not quite, but kind of come close to giving us that. This guy? Why is it there? Yeah, that's there to make sure that suppose this wasn't there. Suppose R was always set to 0. Then this wouldn't be secure even one time. This wouldn't be secure even for a random message. Because, well, you'll get a singular, so the matrix A would be singular. Yeah, the trace of A will give you the message. So R is there. Well, R is there to protect M. If R was fixed, well, M would be revealed. That's the same thing. That's actually, yeah, it's the same thing. Yeah. Right. No. Sorry. No. You have to make sure you have to make sure that A1 and A2 have exactly the same eigenvectors. Otherwise, oh yeah, no, you're right. Yeah, so this would be sufficient. Yeah, even better. So there you go. So that's an even improvement. Maybe that's a way to make it. Maybe there's an idea there for making it 3 times secure. Yeah? Now maybe if we use 3x3 matrices, actually that's something there. So, good things to think about. So just keep in mind that in fact for FHE, one-time symmetric encryption is sufficient. So maybe we can make that faster. All right. So what I wanted to do in the remaining minutes that we have is I wanted to tell you a little bit more about multilinear maps. And in fact, it's something that I should have done yesterday. I apologize. I should show you a little bit about why we're so excited about them. Why are they like the crux of like the most important problem in crypto that needs to be solved right now? So to do that, you laugh, but it's true. This is, I mean, coming up with good multilinear maps is, in some sense, well, the most important problem in the world of crypto these days. Oh yeah. Yeah. That's right. Different talk. Yeah. I'll just use the sentence one now. I'll just say one whenever I mean to say the most important problem. I can save myself a couple of words. All right. So more on multilinear maps. Right. So first of all, the simplest way to state what a multilinear map is, again, is we want these two groups, a group G and a target group, which I'll call GT. Both of these are prime order. They both have a hard discrete log problem. The G and GP both have a hard discrete log problem. And there's a multilinear map between them in the sense, the usual sense of multilinearity. And it's, as usual, got to be efficiently computable and non-degenerate. So that's a multilinear map. It operates on n copies of the group G. I wrote the simplest version of the scheme so that Hendrik doesn't ask me about associativity and things like that. This is the simplest way to describe the problem. There are standard assumptions that we can make about multilinear maps. So for one assumption that we make is what's called the n plus one way decision Diffie-Hellman problem, which is given an n-way multilinear map, you cannot compute an n plus one product. Yeah, you can't compute a product of n plus one elements in the exponent. In other words, if I give you n plus one exponents, if you had an n plus one way map, you could compute this thing. But since you don't, not only can you not compute it, you can't even distinguish it from a random element. Okay, so that's the decision Diffie-Hellman problem in the context of multilinear maps. Is that clear? You can compute a product of n elements, but you cannot compute a product of n plus one elements, and you can't even distinguish the product of an n plus one elements from just a random element. Okay? It's a standard assumption that we make on these groups. So for n equals 2, we have the Weil pairing. For n bigger than 2, we have these beautiful examples of candidates of Garg, Gentry, and Levy, and several others since. These are noisy candidates, and also they require kind of what we call trusted setup, in that someone trusted has to set up the parameters for the scheme, and then he has to forget what he did. If he doesn't forget what he did, then this assumption will be false, and in fact, certain things will go wrong, as we'll see. So far, so good? Yeah. Yes, please. No, I didn't apply. No. This is n. This is n of these guys. Yeah. There's a little n. These 3 dots represent n minus 3 elements. Yeah. Thanks. That's a really good point. Yeah. Okay. Any other questions? Cool. So yes, is it clear for n equals 2, we know how to do this, and in fact, this assumption holds as far as we know for the Weil pairing. So with n being equal to 2, this presumably holds for the pairing. And the question is, could we do this for n bigger than 2? And I would say, like, the first kind of hurdle to get over is, can we do this for n bigger than 2, at least without a trusted setup? So just do this so that the parameters are public and no one trusted needs to generate those parameters. So no secrets are involved in generating these groups. Just like in the case of the Weil pairing, we generate, a pairing-friendly curve. There's no secrets involved in generating a pairing-friendly curve. Okay, so let me give you an example application for multilinear maps. And the problem is what's called multi-user key exchange. So here's the problem. I can explain it very easily. So we have these people on Facebook. They each have a secret key, and they post to their public profile, they post a corresponding public key. And now a bunch of them want to get together, and they want to generate a group key. So 4 of them want to get together, and they want to have a shared key that no one but these 4 will know what the shared key is. So what Bob will do is he will collect everybody else's public keys. So he has his own secret key and the 3 other public keys, and he will use that to generate their group key. Charlie is going to do the same, and he's going to generate the group key. David will do the same, and Ethan will do the same. Okay, so each party is going to collect the public keys of all the other parties, and using its own secret key, will be able to generate the group key. Oh my God, sorry. No. No, we got the. Geez, yeah. My mistake. Yes. This should have been. This is really Charlene. Yeah. Okay, so this question of so this is called multi-party key exchange. It's sometimes called a non-interactive multi-party key exchange, because you notice they never talk to each other. All they do is they read. Yeah, well, they really never talk to each other. That's right. They just read each other's public keys, and from that they're already able to deduce the group key. So they never really communicate. So this problem is like as old as the hills. It's an old, well, some hills. It's a long-standing problem in crypto. You know, the two-party case was solved by Diffie and Hellman just when two people want to generate a shared key. The three-party case was solved by Zhu using the pairings. This is actually what introduced pairings to crypto. So three, and I'll show you how this works in a minute. So three parties can do it using pairings. And the question is, can we do it for any n bigger than 2, for any n bigger than 3? And so, again, using the multilinear map of Garg, Gentry, and Halevi, finally we had a solution for n parties. But because the multilinear map required a trusted setup, this means that whoever set up the multilinear map could actually expose everybody's shared keys. So he could compromise all groups in some sense. So this is the problem with trusted setup. And I'll tell you kind of the last step in the story is finally now we have this huge hammer called the Indistinguishability Obfuscation, which I'll tell you a little bit about later, allows us to finally solve this problem without setup. And so finally we have a solution, but this is really using really big hammers. And today, if you try to implement this, it would take 2 to the 200 years to run. So not particularly constant time, but 2 to the 200 years. Okay, so let me explain how the key exchange algorithm works. If there's one thing you get out of these multilinear maps, let me show you kind of this one really nice application for them. So of course, the secret keys are going to be exponents, and the public keys are going to be exponents raised to group elements raised to those exponents. And now the way we do key generation, so we have our group. The way we do key generation is as follows: every part, the group key is going to be a pairing, tripling, whatever a tripling of G with itself raised to the product of these 4 elements. Yeah. So we only have so that's what the group key is going to do. And how does each party compute this? Well, you can see what. Let's see. This would be, so you take Alice. Now you're in all of a sudden. Kicked out Ethan. Good. Excellent. So this thing needs to be shifted. Okay, never mind. Pretend like this is shifted over here. So it's Alice, Bob, Charlie, and David. So that Alice is happy. Okay, great. So the way Bob computes the group key is he takes Alice's, Charlie's, and David's public keys, pairs them together, and then raises the result to the power of RB, and to his secret key, the power of his secret key. And by bilinearity, you know that these two are equal. So now you can see how each party, is it clear? Each party can now compute the group key simply by taking everybody else's public keys, tripling it or pairing it, and then raising it to the power of its own secret key. Yes? So this is how they all generate the group key. And the question is, why is this secure? And the answer is, well, if you have a 3-way multilinear map, we said it's going to satisfy this 4-way decision Diffie-Hellman problem. So in other words, actually computing this value to an observer who does not have either RA, RB, RC, or RD, this value is going to look indistinguishable from random. Yeah, so this is the power of these multilinear maps. Yeah, they allow us to do group key exchange in a way that an adversary can't figure out what the shared key is. So does that make sense? I just wanted to give you like one application for these multilinear maps, so you see why we're so excited about them. So far, so good? Is this clear? Really easy to explain and a simple application. Any questions on this? No? Okay, cool. So as I said, the current candidate for multilinear maps requires a trusted setup. And the fact that it requires a trusted setup means that whoever set up this multilinear map can actually figure out the key for himself. And in fact, he can figure out the key for any group of users. So you wouldn't really call this a trusted key exchange mechanism if there's some other party out there that can figure out every group's secret keys. So that's the problem with the trusted setup. And so I would say, no, first challenge is, can we have multilinear maps without a trusted setup for n bigger than 2? So challenge number 1 for you guys. Yeah, yeah. Why is it identity-based key exchange? Oh no, this would be a key escrow. It will be a key escrow key exchange, not identity based. What it's not identity based would mean that your public key is your name. And that's not the case here, right? Yeah. So there are people here from the NSA, so I need to be careful with the jokes I make. But in principle, you can imagine, NIST. Okay, let's pick on NIST. No one here is from NIST. I'm being recorded, so I need to be careful. Okay. Okay. So somebody you can imagine would publish kind of parameters for this multilinear map. And then any group can generate parameters, but that somebody can then figure out what the secret keys are for all the groups. So this would not be encouraging for people to use. So the first challenge is, can we have multilinear maps without trusted setup? All right, so I told you that, in fact, we can solve this problem, but we have to use a big hammer called obfuscation. And so if it's okay, I was thinking of telling you a little bit about obfuscation in 15 minutes. See if I can do it. And so, but I need to know to make sure this is actually what you guys want to hear. So how many of you actually know about obfuscation and what's been done in obfuscation? Not the cryptographers? Not. Okay, so hopefully this will be useful to you. All right, so obfuscation is the number one. The most important thing that's happened in crypto in the last couple of years. Yes? Yes. So what is code obfuscation? So the goal basically is to write code such that the code for the software reveals nothing about its behavior, nothing about the program itself, other than its input-output behavior. Yeah. So here there are these contests every year. Here you have like a JPEG decoder that's kind of obfuscated. So presumably it's hard to understand how it works, but not really. This is more of an ad hoc obfuscation. Our goal is to make it so that nothing should be revealed about the inner workings of the code. Basically, there might be secrets embedded in the code, and you should provably not be able to reveal secrets that are embedded in the code from the code itself. And the question is, how do we actually do this? Can we obfuscate? So first of all, what does it mean to obfuscate? And second of all, can we obfuscate programs in a way that you can never extract secrets that are embedded in the code? So why is this so hard to do? Well, so basically when you give the adversary a program that has secrets embedded in it, the adversary can actually, he can look at how long your program takes to run. He can look at the internal state of your program as it's running. He can even take your program and kind of deliberately cause it to malfunction and see how it malfunctions, and that might tell him about secrets that are embedded in the code. So he has like an enormous amount of power, and yet, despite all this power that he has, he should not be able to figure out what secrets are embedded in the code you just gave him. And so I guess we like to say it that, the adversary can read your mind, and still he shouldn't be able to figure out what it is you're thinking about. And even worse, the adversary can even tamper with your mind, and even though he's tampering with your mind, he still shouldn't be able to figure out what it is you're thinking about. And I should tell you that, in fact, there are papers that show that there are obfuscation schemes, ad hoc obfuscation schemes, that if you cause the code to deliberately malfunction, you can actually figure out what secret keys are embedded in the code. And this is using something called fault-based analysis, fault-based cryptanalysis. So so the big breakthrough happened with this, first of all, understanding what obfuscation is. This is mathematical obfuscation. So there are lots of ad hoc tools on the market. This is something that the world really wants to use, lots of ad hoc tools, but none of these are actually, none of them would have cryptographic strength, right? They all admit that with enough work, an attacker can actually recover secrets that are embedded in the code. So the first question was to understand, what does obfuscation actually mean? And so this is a classic paper of Barak et al. Apologies to Kristen, this is just too many names to write out. Barak et al., I'll just say, that defines the notions of obfuscation, and I'll tell you more about these notions in a minute. And then Garg, Gentry, Halevi, and Mariana, Sahai, and Waters finally gave the first example of a candidate obfuscator using multilinear maps that were built before. Okay, so I want to show you very briefly how these things work. The first thing we have to do is understand what is actually secure obfuscation. And so the first definition that comes to mind, so if we're going to build something and prove that it's secure, we need to have a definition to say what it is we're trying to build. And it's not so obvious. How do you define what does it mean to obfuscate code? And so there's the first natural definition that comes to mind is the following one. It's what's called virtual black box obfuscation. And that definition here, let me explain it to you in kind of 1 second, is the following. this is your obfuscated code, right? Your program has been obfuscated, and the adversary gets to work on your obfuscated code. He observes the obfuscated code. Now, he's going to munge and crunch your code in various ways, and he's going to produce a certain output. What you'd like to say is that for every adversary, there exists a simulator that is only interacting with the code as an oracle. So it's only providing inputs and looking at the outputs. So it's only observing the input-output behavior of the program, and yet it's able to produce exactly the same output as the adversary who's actually given the code. Okay, so for every adversary, there exists a simulator that does exactly what this adversary did, but only using input-output behavior. So because the simulator exists, this means that the adversary didn't learn anything about the code beyond its input-output behavior. Right? That's what the simulator proves. If you can do everything you can do with the code, you can do without the code. That means you didn't learn from the code anything beyond what you could have learned just from its input-output behavior. Okay, so that's kind of the first definition, right? An obfuscator is secure if for every adversary there exists a simulator. Unfortunately, it turns out this is too strong a definition. There are some programs that just cannot be obfuscated. And so we'd like to weaken our definition somehow and come up with a realizable definition, and that's actually the one that's taken over the world, called indistinguishability obfuscation. Okay, so IO, indistinguishability obfuscation. So the point of indistinguishability obfuscation, it's a much weaker notion, but as far as we know, it's realizable. And it says the following: if I give you two programs that the programs themselves might be different, but they compute exactly the same function. Okay, so these two programs are identical. I mean, as far as their input-output behavior, it's identical, but they might be implemented slightly differently, right? I mean, one might add 1, and the other one might add 2 and then subtract 1. These are two implementations of the increment by one program. The obfuscator, what it will do is it will generate obfuscated code, and the point is that the obfuscated code that's generated looks the same whether it came from P0 or from P1. So if the programs are the same, once you obfuscate them, you can't tell whether they originally came from P0 or originally came from P1. And if that's the case, then we say the obfuscation is secure. And if you think about this looks like kind of a bizarre notion of obfuscation. How is this obfuscation at all? This is not really hiding anything. It just says you can't tell which program was obfuscated, but the programs were the same to begin with. So why does it really matter? I mean, the programs were different, but they were computing the same function. So why does it matter that we're able to obfuscate these? And surprisingly, there's this result of Sahai and Waters and many other people since that show that in fact this is sufficient for most of the applications of obfuscation. So this has been kind of initially this looked like it's kind of not that interesting of a definition, but it turns out this is kind of at the heart of everything we want to do with obfuscation. So this is. Then it would be trivial to obfuscate. Yeah. So if you have a set of functions that has a canonical representation would be trivial to obfuscate. So those are not interesting. Those are not interesting to obfuscate. That's right. If you could compute that, but generally that's a sigma 2, and that's like a even harder problem than P. Yeah. Very good. Yeah. So you would think that this is not a good way to obfuscate, right? Because if you have a point function, then it's a canonical representation, and it sounds like it's a good obfuscation. But of course, it doesn't satisfy our natural notion of obfuscation. So you would not apply this kind of notion to point functions. Yeah, that's exactly right. Yeah. So you would not apply I/O to point functions. In fact, you apply the obfuscator to more complicated functions. Typically, what you apply them to is maybe they have two keys and they can choose to decrypt using a left key or a right key. The two keys do the same thing, one program decrypts using something on the left, and one program obfuscates using something on the right. And because of the obfuscation, you can't tell which key was used to decrypt. That's how these things are used. Oh, that depends. So you're making okay. So the assumption was if given a program, you can find a canonical representation of that program, then you would have immediately you would have I/O obfuscation. Mm-hmm. Actually, what you're proving is that for point functions, there will be some programs that you will not be able to make canonical. Yeah, so the canonical representation of a point function is just check equality to the point. And you're saying that there are some implementations of that point function which cannot be made canonical in polynomial time. So the obfuscator that Oded is describing actually can't be implemented in polynomial time, right? But even for point functions, that's kind of the consequences. Oh, the obfuscator always runs in polynomial time. That's a requirement. Oh, actually, unbounded obfuscator is equivalent to VBB. Yeah, that turns out to be not realized. We can't obfuscate under those settings. Yeah, so that's a different. Yeah, so we're going down. That's a complexity discussion. So let's unwind a little. All right. So we have this notion of indistinguishability obfuscation. Yes. Oh, sorry. Thank you. Yes. When I write indistinguishable here, what I mean is in the cryptographic sense, which is the obfuscator generates a distribution on possible outputs on the left, and it generates a distribution on possible outputs on the right. And these two distributions should be indistinguishable under an appropriate complexity assumption. Yeah, it's indistinguishable in the cryptographic sense. Yeah. Thank you. That's a good point. Okay, so fine. So let's look at how we actually construct these obfuscators, and this is the work of, as I said, Garg, Gentry, Levy, Mariana, and so on. And so the way the obfuscator works is essentially in two steps. First thing that we do is we obfuscate shallow formulas. So technically these are called NC1 formulas. So we obfuscate shallow formulas. And the next thing we do is the next thing they do is they show how an obfuscator for shallow formulas is enough to actually obfuscate everything. Okay, so I'm not going to show you how the boosting works. I'm just going to talk about the obfuscator for shallow formulas. So when I say a shallow formula, here you have a formula, right? You can see this is a relatively shallow formula, and it's able to convert this formula into an obfuscated code. And so let's look at how the obfuscator for shallow formulas work, and you'll see where the multilinear maps come in. And I'm going to do this at a very, very high level. There's lots and lots of details that are going to go into this. I'm not going to go into all the details. I just want to show you at a high level what the obfuscated code looks like. So here we have our formula of depth D. The first thing that we do is we take our formula and we apply this conversion called Barrington's theorem that takes an arbitrary formula of depth D and converts it into a product of 4 to the D matrices. So it's exponential in the depth, which is why why this can only handle low depth formulas. So what is when you convert to a matrices, what does it actually mean? So basically you output pairs of matrices. Okay, so each pair of matrices is associated with one input wire. And then, so you have 4 to the D matrices. Each one of them can be very short. It's like these are 2 by 2 matrices. Okay? And then each pair is associated with an input wire. Now, for a particular setting of the inputs, you choose one, like 0 means up and 1 means down. So for each setting of the input, you choose one particular path through this, through these pairs. You compute the matrix product, and you compare that to one fixed matrix. If the equality holds, you say the output is 1. If equality doesn't hold, you say the output is 0. Okay, so that's step number 1. Basically, we take the formula and we write it in matrix form. Okay, and there's a theorem that says that you can take any depth D formula and write it in matrix form like this, where you need 4 to the D matrices. And this is, by the way, a beautiful application of non-solvable groups. Yeah, it's actually using, well, here I'm using 2 by 2 matrices, so actually I'm using SL2F for some finite field. The original Barrington theorem was using the symmetric group of S5. But it turns out, yeah, these matrices essentially correspond to some non-solvable group, and any depth D formula can be written as a product of 4 to the D matrices. Yeah, I'll skip the story. There's a good story there, but I'll skip. All right. What? Yeah, interest of time. Good. So that's step number 1. We took it. We wrote it as a bunch of matrices. So you should ask me first of all, why do we use matrices in the first place? Well, this might already look obfuscated to you. This like looks, it's got nothing to do with the original formula, but it turns out this is not an obfuscation. This you can actually invert and recover. From this you can actually recover whatever secrets are available. So that's not enough. The next thing we do is we're going to randomize all these matrices. So each matrix is going to be randomized on the left by one matrix and on the right by another matrix. And you notice these are the actual matrices that are going to get published in the obfuscated code. And you notice that when we do, we're using the same R1 in both the top and the bottom matrices. So now when we take the product of consecutive matrices, you notice that these R's cancel, and we actually get the original product of matrices. Okay, so the nice thing about doing this is now we've made the program not contain the original matrices, but just kind of random looking matrices, and there are many, many of them. Okay, so this making progress towards obfuscating the code. Turns out this is still insecure. Is this clear, how the fact that this randomizes all the matrices? Turns out, yes, so we've randomized all the matrices. Now we got kind of pretty random looking code. Turns out this is still not something that you can prove is IO secure. There's still attacks on this scheme. But is it clear what we've done so far? Yes, we've just taken our matrices and we've randomized them without affecting the output. Yeah, this still allows us to evaluate the program. And the last step that we do is basically we take all these matrices and we put them in the exponent. Yeah, so we encode them for a multilinear map. So now this matrix is available in the exponent, and this matrix, say, is available in the exponent. And when we want to multiply these matrices, what we do is we use the multilinear map to actually compute the matrix product. Yes? So this is why the multilinear map is so important, because it allows us to essentially encrypt these matrices, still compute all the products, and at the end test whether the final result is equal to a fixed value. Yeah, so basically if I have g to the power of a matrix and g to the power of another matrix, I can pair these two, and I'll get g to the power of the product of the matrices. Yeah, I mean I would literally do the matrix multiplication using pairing. Yeah, so literally multiplying rows by columns. And I would get g to the power of a times. Yeah, and if I have an m linear map, then I can do a product of m matrices. And in fact, what I would need is a 4 to the d linear map. Right? So that's why we need a multilinear map of very high degree. Exactly. G to the a itself will tell us what the original matrix is. So G to the R basically makes it impossible to mount the only attack that was possible to do after the matrices were rendered. All right, so this is at a high level. I just wanted to show you that where the multilinear maps are used, what the obfuscated code looks like. So it's basically these randomized matrices placed in the exponent of a multilinear map. And then when you want to evaluate the code, you basically evaluate the multilinear map to compute the product of matrices and check whether the final result is equal to a particular output. Okay, so that's how you evaluate the code. And the theorem basically says that under an appropriate assumption about the multilinear map, it's a bit of an ugly assumption, but under an appropriate assumption, in fact, this implements IO obfuscation. So that's where all the excitement is about. Now, why is IO obfuscation so exciting? Turns out it pretty much solves everything under the sun. Yeah, so you can see IO is the sun here, and everything else is underneath it. Yeah. So yeah, lots and lots and lots of applications. There are more and more coming out every day. These are things that we had no hope of doing in the past. So these are all applications that came out in the last 2 years, things that we simply couldn't do before. And now they're all being kind of solved by this hammer, except this hammer, remember, each one of these runs in constant time, but the constant is 2 to the 200. So that's where we are today. So I was going to show you how to do multi-user key exchange, but I think I'll stop here. Great, thanks.